using SOLIDWORKS Simulation Express. And Simulation Express can help you do finite element analysis on a single part. So if you have one part that you want to find out if it's safe enough or not, you can do that for free. Then I was going to also show the advantages of the full simulation package because it lets us do a little bit more detail with parts, and it also lets us get into assembly simulation. So if we had a whole assembly that we wanted to try to simulate and figure out if it would work or not, we can do that. So in case you didn't meet me last time, just a little bit about me. I've been a teacher with Trimec. It's a global company that sells SolidWorks. We're not in Uganda yet though. But I've been a teacher with them for 3 years. That's where I learned all these skills. And I became a certified SolidWorks expert with Trimec and a certified simulation professional so far. I teach 2 of our sim classes, but we have some more that I don't teach yet. So there are still some areas that are kind of unknown to me, but I have friends that I can ask about that stuff. Before I was a teacher with Trimec, I was a mechanical design engineer for about 15 years, and I really love 3D printing. All right, today we're going to do an overview at first. Just what is this going to do for us? What are we asking it to do to the model? And roughly what kind of math is it doing? We're not going to get too far off into the math. Then we'll show the free tool Simulation Express, and we'll test out a hand wheel and see if it's going to be strong enough. If we pushed on it, it might not be strong enough. It might break. So we'll figure that out. And then we'll take a look at the full-on simulation package. You do get a simulation package. If you buy SolidWorks Premium, it comes with the ability to do static simulations like we're going to show. Sorry, I slid back in my slides there. So if you have SolidWorks Premium, you can do the tool that we're going to show. If you buy Simulation Professional, you can do even more with it. You can do different kinds of studies like frequency and thermal and a bunch of different things. Then we'll take a look at using the sim packages beam and shell mesh inside of an assembly. I have an assembly file that it has some easier ways to mesh things that we're going to take a look at. So let's get into this overview at first. Imagine if we had to measure this long, windy brick road. Imagine if we just had a meter stick to measure it. And we were going along and measuring it. Well, that's 1 meter, that's 2 meters, 3, 4, 5, 6. You can see when we get to some of these bends, we have to kind of cut the corners a little bit due to the size of our measuring stick. If we had a roller, like a little short roller instead of a meter stick, we'd get a different answer if we measured this, most likely, because we'd measure around the inside of the curve better and that kind of stuff. And the best yet, maybe we have a roller wheel that measures as it rolls, and we could get a really accurate measurement. If we rolled along and measured on the inner edge of this thing, we could get a really accurate measurement. But the size of the tool that you're measuring with is going to affect how accurate your answer is. Now, when we make an FEA model in SolidWorks, we break it up into a mesh. And the mesh is sort of like this brick road. If our mesh isn't tight enough, it's going to cut some corners and our answer won't be precise. So the tighter your mesh is, the closer that you're going to be to a real world answer. But it also takes longer for the computer to think about it. Now let's discuss. So we start with a CAD model and we want to know, is this thing strong enough to work in the field, or do we have to change it up a little bit? Well, at first, we probably want to simplify that model a little bit. There's some fillets here that aren't going to really affect the strength, these ones on the outer edges. So we would make a configuration that's simplified a little bit to help the mesh be even simpler. Then we would take this into a simulation study. We'd choose what type of analysis we want to run on it. There's different ones, but the one that we're going to show is a linear static analysis for all the different things. Then we'd add a material. Make sure that it has a material on it. The materials that are in SOLIDWORKS have mathematical quantities that will help it solve the stresses. So make sure it has a material. Then we have to give it supports. Inside SOLIDWORKS, at first, it doesn't know how this thing's held down. So we'd have to say like, oh, the back wall of this thing can't move. Then we'd add any loads or pressures. Maybe there's a force pushing down on this thing. We'd add that in, so SOLIDWORKS knows what it's dealing with. And then we'd tell it, hey, mesh the model. Break this model up into a bunch of pyramid shapes. The little pyramid shapes, each line on those is kind of like a spring. If you want to think of it like a spring, that's how the math calculation works. There's two types of solid mesh, but each little pyramid is called a node or an element. Each little pyramid is called an element, and each of these little red points is a node. There's a draft quality solid mesh, which only has 4 nodes. And there's a high quality solid mesh that puts mid nodes along the center of those springs, so we get more nodes. At the end of the day, how many elements and how many nodes there are determines how long it's going to take our solver to solve this problem. So it does pay to try to keep it simpler if possible. We won't have to wait as long. That's why we don't always just mesh it as tight as we can go from the beginning, because sometimes it could take over an hour to run a sim for a simple thing if you have a really tight mesh. After we break it up into this mesh and all these different elements, SOLIDWORKS will take it and run a large matrix and solve the matrix for all of these nodes. It's trying to figure out where the nodes are displaced to. And after it solves all of those, it then solves for stresses and strain, and it gives us color-coded charts to look at to show us where the high stress points would be in our model. If our model can't handle it, we'll see that the stresses that we see are over the yield strength of the material, meaning it would break. So here's kind of what it's doing with these nodes. So imagine each of those lines is a spring, and each of the red points is a node. The nodes are these x1, x2, x3. Imagine if we wanted to figure out how much x3 moved, we'd have to use the spring formula to calculate the displacement of each one, and then we'd know how much that one moved. So this is kind of what SOLIDWORKS is doing, but on a much greater scale. It's using a big matrix and solving it all for us for all of those points in this whole entire mesh. Now, let's talk about what linear static analysis means. So a linear static analysis means that we are looking at a material before its yield point. If it goes after its yield point, we will still know that it's seen a higher stress, but we might not know exactly how much it displaces because it might actually break in real life. So if it's up here, we'll still know that it broke the material, but this kind of analysis is designed for the linear straight section of the stress strain curve of a material. If you have a material that's real rubbery or something like that, this isn't a good type of analysis to use if you were trying to see how much a tire could bounce or something. That would be a nonlinear study. And if you wanted to see like a crash test or something like that, that would be a nonlinear study also. So this linear static also means that it's just one instance in time. We're starting with that bracket already loaded. We're not saying, oh, it's loaded for 20 seconds. Does it break? It's just right now. If it's loaded with this, how is it doing? If we want to involve time in there, that would be another reason that it's a nonlinear study. So if we wanted to know, oh, if I put this load on for 10 seconds, pull it off, put a different load on for 20 seconds, well, that's a nonlinear study then. And if we had a rubbery material or like that metal that when it heats up, it takes its original shape back, or soft plastics, or metals that are way beyond their elastic limit. Like if we want to see how much they stay bent after they got bent, we would need the nonlinear package, which SOLIDWORKS can do also. And if we're trying to check anything that's going to bend so much that it self-reinforces, like if you crush a pop can or if you crush a car, it's going to run into itself in areas that we didn't predict at first. So that would be a nonlinear study also. This is going to be for mainly small deformations for a static linear study, but it'll tell us if something's going to break or not still. Now, there is some room for errors in these kind of studies. Let's assume that we drew the part right. Usually the geometry of the part isn't the problem. If you drew the part the way it is in real life, usually that's not the big problem. If you grabbed a material from SolidWorks' database, as long as it's the material that the part actually is and it's not some different heat treat or something, this probably isn't the problem either. So make sure you get the material that you're actually using. Sometimes there's some weird heat treat or something that will greatly affect the strength values. So make sure that that's accurately reflected, but that's not most often the reason that we're inaccurate either. Usually it's either the loads or the fixtures that lead to inaccuracy. With the loads, that's like the forces and pressures that we're going to add to the model. A lot of the times we forget about things that are happening in the real world, like, oh, we didn't apply gravity, but gravity is going to have a big effect. If you forget it, you're not right. So like, think about all the loads on the system. A lot of times you're kind of guessing on these things too. So like, oh, that motor weighs this much and that thing weighs this much, and how many newtons would that equal? A lot of times it's an approximation, so those could be a reason that we're wrong. So go back and look at your loads and make sure that they are real world loading. And then where we tell that model to be held down by, like on the bracket where I said maybe the back of it would be held against the wall, the fixture. The fixturing is the most often cause of problems with simulation because it can add artificial stiffness to a model. If you have a plate with 4 holes in it and you tell it that all those 4 holes are fixtured down, it's not going to be able to move in between. It adds artificial stiffness to fixture things down. So be careful with the way you fixture things. There are special fixtures that you can use where you can lock things down only in certain directions, as if a hinge, or you can even specify the directions that you want to lock it down in with the full sim package. So usually it's the loads or the fixtures that make inaccuracies. We recommend that you run multiple studies where you change some things up and make sure that your answers are similar. If you get greatly different answers, that means that you don't have convergence. We want to run more than one study to know that we're right. Usually we change some little details. Maybe we make the mesh a little bit tighter and run it again. And if we get a crazy different answer, that means that the model diverges and doesn't converge. meaning something's probably wrong with our setup. So we want to try to make sure that we converge on a certain number. And here's the different ways that we can use simulation in SOLIDWORKS. The first one, that's Simulation Express. It's free. You just have to have a 3D Experience ID. So you have to set up your online account with SOLIDWORKS. It's like registering your software, but this is free to use, and it can do single parts with simple loads and supports. You don't get a whole lot of options for the loads and supports. Then the next package up beyond that is you could buy Simulation Standard. That'll allow you to do linear static analysis of parts and assemblies and have much more control over the meshing and the loads and supports. Then we have Simulation Professional, which lets you do linear static analysis, as well as thermal studies, buckling studies, which are really important if you're making tall steel structures, frequency studies, also important for those big steel structures to make sure you don't hit some natural frequency and make it resonate. That would make it fall down. You could run drop test studies and optimization studies, and also fatigue analysis studies with Simulation Professional. And we have Simulation Premium. This will open up those nonlinear studies for you. So if there's anything you want to do that might involve time or a rubbery material, that kind of stuff, you're going to be in the nonlinear end of things. All right, so our first example, we're going to take a hand wheel, and I'm going to go into the Evaluate tab on SOLIDWORKS, and I'm going to turn on the Simulation Express Analysis Wizard. It's going to make a analysis wizard show up on the side that'll help us set up this feature tree for the simulation study. Every simulation study has a feature tree, and it also has a corresponding tab across the bottom that you won't see unless you have the simulation tool added in. So you'll get to see how this works in a second. We're going to try to see if this thing is strong enough, or if we have to go back to the drawing board and change something about the design. Maybe we'll have to make it have extra spokes and try again. Let me get into SOLIDWORKS here. And I noticed there's like a line that got drawn on the screen. Let me just see what I can do about that. Not sure why this line's on our presentation. It's not going to affect things too bad. Let me see, annotate, erase. Yeah, maybe I did that by accident. Okay, we got it now though, it's erased. All right, okie dokie. So let's say we have this hand wheel model here, and we want to find out if it can hold up to someone pushing downward on it with 3,000 newtons of force. We don't know that just from looking at it, but we could use the Simulation Express add-in to have SOLIDWORKS push on this thing and let us know what kind of forces it's seeing. Now, I've already added a material to the feature tree. In SOLIDWORKS, it's cast alloy steel. If we want to have a different material, we could add that here. We could also add it when we're doing the simulation study. They could be different materials than the original part. That could be something we're trying to study. Maybe a better material might be a good option. So if I go into the Evaluate tab, and then I go to our Simulation Express Analysis Wizard, it's going to open up the studies that I ran the other day. and it's going to say, hey, if you want to clear these studies out and start a new one, just hit start over. Okay, I'll start over. It'll delete the ones you already did. Yeah, that's okay. All right, now the tool starts from scratch, and it says, hey, apply some fixtures to your model. We just have to click add a fixture. And it comes up over on the left-hand side in the property manager. We can only add one type of fixture here. This is a big difference from the full package. We can only add fixed geometry, which locks down all 6 degrees of freedom. It locks down translation along every direction, as well as rotation along every direction. So I'm going to say this inner edge here is fixed. Maybe that's where it's bolted to the machine. That's our fixed geometry. That's not going to move in this test. And I'll hit the green check. We could have more than one fixed area, but if I fixtured here and out here, that would be a no-no, because that would not allow this to move. That would add artificial stiffness to the model. We wouldn't want to over fixture things. All right, now if we wanted to add any more fixtures, we could hit add a fixture. We could edit the one that it added here. It added a fixture in the feature tree. See that fixed? We could edit it, or we could just hit next to add the next thing. Now it wants us to add any pressures or forces to the model that we think it's going to experience. In this case, I think it's going to see a force. So I'll say add a force. I'll grab this inner circular face. And at first you can see the force is kind of pushing in all the directions. I want it just to push down, like someone's pushing on this handle. So we could tell it, oh, we want to go to apply a selected direction. And then I could give it a plane or a planar face. Let's say the right plane. Now all those little arrows are pushing normal to the plane. So it's like it's being pushed down on with someone trying to push that thing. Now let's say there's 3,000 newtons. I could type it in the little flag here or over in the box over here. Let's say there's 3,000 newtons. And I'll hit the green check. We could have more forces. We could have more pressures. We could have forces and pressures. There can be more than one of these things, but in this case, there's only one. So I'll hit next. And if we wanted to choose a material, it says there's no material assigned to this part. For whatever reason, it lost the one that I told it to be. So I'm going to choose a material, and we'll pick a material from SOLIDWORKS' database here. And these are the values that it really needs. All these red values, elastic modulus, Poissons, it shows the values that it needs for this study in red. The blue ones, I think, are for some other types of studies that you might want to do. But this is all the data. If you tried to make your own material, you can. You just need to know this kind of data about it, and you can fill it out too. There's a pretty extensive list of different materials that comes with SOLIDWORKS, though. It's pretty detailed in here. So I'm going to apply our cast alloy steel. I'll hit apply and close. And now it knows the math numbers it needs to help it solve this big matrix after it meshes this thing. Then I'll hit next. And if we just hit run, it's going to run with a generic mesh size. We won't know how big it is. If I hit change settings, I can change the mesh density. If you're using this tool, I would always recommend hitting change settings, change mesh density, and making sure you drag the slider all the way to fine. If you check on the mesh parameters, you could even decrease the mesh size in here if you wanted to. You could type a value in here. Maybe let's say Oh, we want a mesh size of a maximum element size of 3 in this case, 3 millimeters. You can see there's not a whole lot of options in here. There's a mesh quality area. We could have high or draft quality solid mesh still. Remember, the only difference was high quality has one more node on each element, on each leg of the element. So it's got extra nodes in the middle. That's why it shows the little squiggly triangle versus the normal pyramid. We could still have that, but there's not a lot of other options in here. Whenever I use the full simulation package, you're going to see how much more control we have over meshing. This is why it's better too than the free one, because if you don't have a lot of control over the mesh, you don't have a lot of control over your accuracy. In the full package, I could say, oh, these fillets need to have an even tighter mesh than everything else. And I could mesh the whole thing with a looser mesh. We don't have that kind of granular control when we're running Simulation Express, but we'll still get a pretty reasonable answer. Let's hit next. Now it's going to mesh this model. There's also tools in the full simulation package that help you determine if your mesh is good or bad. And in the full simulation package, SOLIDWORKS can make the perfect mesh for you. You can tell it, I want a mesh that's 99% accurate, and it'll check it and make sure it is. So, all right, so mesh failed. Let's reduce mesh size. There's apparently some areas here that are even tighter than that, and it can't go in them. So let's try a 2 millimeter mesh. It's not going to be as clear with how it fails in here as the full package either. The full package will come up and show you where it fails and help you refine it. So apparently I just didn't make my mesh tight enough. All right, it worked that time. Now we actually see the mesh on the model. See how it's all triangularized now? This is called a solid mesh because it uses the whole entire pyramids as an element. We have simpler types of mesh that I'm going to show later, but you can see that mesh, it's going to have to solve along each of these little line segments whenever we solve it. That's how it's going to know how to color code things. So I'll hit next and I'll run the simulation. And it takes a moment here. It's going to try to show us how this thing would deform with an animation. If the animation looks funny to us, if it's not the way we think, we should go back. We should change how it's fixtured or change the way the forces are applied and then run it again until it looks like we think it would. Let's give it a minute here though. That you can see this tight mesh everywhere is going to make it take a while. With the full package, we could have said, oh, this area around the wheel doesn't need to be so tight. All right, it's getting there. It's doing its thing. Now it's starting to play the animation. So give it a second. It'll get smoother here. It thinks that this thing's gonna deform like it's showing. It thinks it's gonna do this. The way we have it fixtured, the way we have the forces applied, it's gonna deform something like this. I would say that seems pretty accurate. That's probably what I was thinking anyways. So let's say yes, that's the way we think it's gonna deform. Yes, continue. If not, we could say no, and we could go change up the fixtures or the forces until it looks like we thought. I'm gonna say yes. And now the first chart it shows us is the factor of safety plot. Anytime we have a factor of safety below 1, that means the design is going to break. So our lowest factor of safety in our model is 0.5. And it shows us in the plot where we went below 1. So any of these red areas, I would say it's probably likely to break in here first, where the most red is. This would break the part, and we can be pretty confident it's not strong enough. Most of the time, people want to build something with a factor of safety above 1. If you get in an elevator or something like that, and you see the weight rating is 1,000 pounds, oftentimes elevators have a factor of safety of at least 4. So that would mean it would actually take more like 4,000 pounds to break it instead of 1,000. So if it's below 1, that means it can't handle the force that you put on it. All right, now we could even look at the stress that this is seeing. I have this results folder since we've ran it, and I can just double click on these to see the different plots. If I double click on the stress plot, or if I click show von Mises stresses over here, it's going to do the same thing for us. It'll take us to this plot. And we can see that we've surpassed the yield strength of the material by quite a bit here, almost double. So the yield strength of our material is about 241 megapascals. We went all the way up to 481 at the red areas. Very similar to how we saw on the factor of safety chart. The same areas that we saw before, those are the ones of concern. So it's probably going to break in here first. If we hadn't surpassed the yield strength, that would be a sign this might work. But since we've surpassed the yield strength, I would say we have to go back to the drawing board. Now, there's another chart we could look at, the displacement. How much would this thing actually move with this force on it? But remember, it could have broken. So this might actually be on the ground. In this instance of time that SOLIDWORKS calculates, it doesn't calculate if it broke or not all the way. It won't tell you if it's on the ground. If you're below your yield strength of the material, then the displacement result is very accurate. So it says it moves about 0.5 millimeters, but in real life it might have broken and be on the ground because of surpassing the yield strength and being so much lower than 1 with the factor of safety. So we know we'd probably have to go back to the drawing board for this one. We could say done viewing results, and then we could have it spit out an eDrawings file if we want, or generate a Microsoft Word report. An eDrawings file is a 3D model that people can look at that has your results in it. Let me go back for one moment. I'll hit the back arrow, and I'll go to the von Mises stress plot. Maybe we want to show that one to people. So I'll stop on that one, and I'll say done viewing results. I'll generate the eDrawing file, and I'll throw this off on my desktop in the Swug sim file set in here. Throw this off in here. eDrawings is a free viewer that anyone, even if they don't have SOLIDWORKS, can view this in 3D with. I've sent this kind of model over to Germany to show them one thing I found that was concerning before, and well, it makes it look like you're really good at math, even if you just know how to click buttons. So I'm not the best at math, to be honest. I am a mechanical engineer, but that was my least favorite subject for sure. I like the design aspect of things a lot better. So now this is what you could spit out and send to someone. Hey, this is a problem. If we put 3,000 newtons on this thing, we have to go back to the drawing board. It will also help you make a Microsoft Word report. If you generate a report, it'll spit it out into a template. You'll still have to type in your findings, but it helps you out a little bit there. Now, the Simulation Express tool also has another capability that I'm not going to show just because it takes a long time. If we hit next, we could optimize the model. This will let us grab one dimension only. In the full tool, we could optimize something based off of a lot of different things. It wouldn't have to just be one dimension. In here, we could optimize the model and grab a dimension off the hub and have it play with it and run multiple studies to tell us if there's one where it's better. It does take a little while. I'm just going to not do that step here. And I would also not recommend trying to make something down to the wire optimized with this tool because it's not as accurate as the full package. So you could get in the right ballpark anyways, but I would recommend using the full package over this tool for that. And when you're done, you're done. You can X out of the tool and save the results. If you save the results, the next time you come back into the Sim Express study, it'll still have this tree set up. So that's the first example I wanted to show. I do have two more pretty good examples to show. Let me get back to the PowerPoint real quick. Now, in the full simulation package, I have an example that's going to be solid mesh also, but it's going to show you some of the other things we can do. So instead of just having a force or a pressure, we get a lot of different types of loads that we could add. We're going to add a centrifugal force in this one, as if the fan blade's rotating at a certain speed. And we want to see if the fan blade, we want to try to see if it's strong enough, first off. And we also want to see how much the ends of the blades displace whenever it is spinning at max speed. Maybe we're trying to make a hole that this fan blade fits in, and we don't want it to catch the outer edges of the hole, something like that. So we want to know how much the edges of the blade are displaced. We're going to see a couple different things here. With the full entire simulation tool, you can be a lot more specific with your mesh. See how tight this mesh is along the face and how loose it is along here? We couldn't do that with the Sim Express tool. We had to have everything be the same size. Another thing we can do with the simulation package is we can use a different type of fixture here. If we have something that's the same all the way around, we could use a symmetrical fixture. So we only have to mesh just a little piece of the thing. It saves on mesh size. And then in the results area, you can show symmetrical results. So you can't do this kind of stuff with the Sim Express package, but it's a similar feel. We're going to go into the more powerful simulation tool now. So I'll close this one out and I'll open up our fan blade. There we go. And at first you can see I have this nice model. I also have a configuration that's simplified where it's cut away, so it's only one blade. We'll run one on the whole entire model first, I guess, so you can see that. And then we'll show the symmetry setup also. So if I go to my SolidWorks add-ins now, I'm going to turn on the full entire simulation tool. You can see I have a couple different ones. I have the one that comes with SolidWorks Premium. And I also have SolidWorks Simulation Premium, which is the full package. So either one of these will work for this type of study that I want to do. I'll just choose that add-in and I'll give it a second. It's going to give us a simulation tab up here. It's going to also give us a simulation drop down. It just takes a moment. You can see I have some other studies set up down here already. The full blade study. In the Sim Express study, you can only have one study tab at a time. It clears the results out. In the full simulation tool, you can have as many simulation study tabs as you want. They can be on different configurations. I'll go to this cutaway config. You can see we got some results saved on this one too. Now I'll show you how we can set these up. So I'll go back to the model tab. The full simulation tool does include a wizard to help you too. If you like the wizard that's in Simulation Express, you could go under the new study drop down on the simulation tab and choose Simulation Advisor. This knows a lot more information than the Sim Express does. It'll try to help you pick the right kind of study. It'll help you try to pick the right kind of mesh and all the different interactions you might need in an assembly file. It's a lot more powerful than the Sim Express tool is. But we teach in our classes that you can be a Sim Pro and never even touch that area if you want. If you know what to set up, you just, well, I'll start a new study. And I'll call this one full fan. And it's a static study. This is the area that you could set up the different types of studies in if you have the full entire tool. You can see there's a variety of them, even a drop test. If you want to see if something will survive being dropped, you can do that kind of study also. There's a wild amount of studies that you can do. I'm just going to hit OK here with a static study. And now we see we have a folder. The first thing about this model is I have all of these fan blades as a separate body in SolidWorks. If we look at my feature tree, I've got blades and a pattern of them and the hub. We couldn't do this with Simulation Express. Because it's a multi-body part, it gets treated like an assembly. It wouldn't have let us do this with Sim Express. That's the first thing. Now we have a folder here with all the different pieces. We can see what material they're supposed to be. There's nothing on them yet. I could add a material. I'm going to right click the parts folder and add a material to all of these bodies. Let's say that they are some kind of aluminum. I don't know. I'll go under aluminum alloys. Maybe I say it's like 6061 aluminum. Just the top level alloy. No weird heat treats. I don't know. Maybe it's just that one. I'll hit apply. I'll close it. Now we've got our 6061 alloy on all of these things. This first symbol means that it's going to be a solid mesh. We're going to learn later they don't have to be a solid mesh. There are simpler forms of mesh to help you simplify things. This other thing means that they're the high quality mesh type, so they'll have extra nodes in the middle. It takes a little longer to run high quality mesh, but the results are better. And we have this component interactions area now. By default, it selected to bond all these things together. That means that it's going to basically glue these blades to the hub. Imagine if they're one piece then because of bonded. Now, there are some other options that we can control in here. We could tell it to enforce common nodes between touching boundaries. That means on this fan blade part, the mesh is going to have to line up with the mesh that's on the hub. All the nodes are going to have to line up if I do that. That is the most precise way we could do it. Enforce common nodes. You don't have to do that, but you get some control that you don't even have in SimExpress at all. All right, now we could also have changed it to just telling things that they're just contacting one another. Maybe it's like a pair of pliers where it is free to move. We could tell it it's just contacting, and we could even give it a friction value where it's contacting. This is good for this model though. Now I'm gonna add a fixture. I can just right click on the fixtures in the tree, add some fixed geometry, but you can see we have a whole bunch of other types of fixtures now that we could add. That's because we're in this full entire simulation tool now. You can see the first one is what we added in SimExpress. We've got roller slider fixtures. We've got hinge fixtures. We've also got this whole advanced area of fixtures with symmetry. And these last ones are basically whatever we need them to be. If we use reference geometry, we can tell it exactly which degrees of freedom are locked down, which you don't have that kind of control with the free tool anyways. So in this one, we're going to just add fixed geometry to this middle face. And I'm going to add our rotation. I need this axis to add the centrifugal force. I'll right click on external loads and add a centrifugal force. You can see there's a whole lot of other types of loads in there too, though. With the SimExpress tool, we just had force and pressure. Now we could add a torque, we could add gravity, centrifugal force, a bearing load, a temperature, or we could even tell it how far something had to move. Like if we had something that was bent and we said, oh, well, this piece was 1 inch down when we saw it, we could tell it that, and then it could try to tell us how much force it took to get there too. We can have the flow effects come in from a flow study. We can bring the thermal effects in from a thermal study and see how they affect the stresses also. We can have a remote load or mass and a distributed mass. You can see you just have a ton more control in here. We just want to add the centrifugal force to this one. And I'll grab the axis and I'll tell it that this thing is spinning at this instance in time, let's say 400 radians per second. Now you can see we've got a symbol on the model to show us that centrifugal force. Simulation symbols have their own notch under the view eye. You could turn them on and off. Now we're ready to mesh this thing. I'll right click on the mesh folder and create a mesh. And I'll drag the slider towards fine here. Let's say we drag it over there towards fine. Now, before you saw we had a mesh area where we could control that. We have 3 different types of mesh we could use now. In the SimExpress, we couldn't pick which type of mesh. I'm going to use a curvature-based mesh. These are different algorithms for how it's going to go through and mesh your model. And I can see the maximum element size, the minimum element size here. If I wanted to mess with these, I could type a value in. Maybe I say max element size 9, min element size. I think I have some 5 millimeter fillets in there. So 1.8 should be fine. We can also tell it the minimum number of elements around a circle. It has to have at least 8 elements around a circle. I can make that higher if I wanted more precision. And we can tell it a ratio. This is how the elements grow or shrink as they come to a weird area. Let's just see how this mesh looks like when I mesh it. I'll show you how with symmetry it allows us to make an even tighter mesh. So there we can see our mesh now. We did enforce common nodes, so anywhere the fan blades touch the hub, there has to be a node there in that mesh also. You can see kind of how this mesh lines up. If we didn't do that, it wouldn't line up. It wouldn't be as accurate. But that's an okay mesh. It's not going to be as tight as the one we make at the end, though. And the tighter your mesh is, the better your answer is, the closer it is to real world. So let's see, we'll run this study. And it's going through its solver right now. It shows us a deformed result at first. This is exaggerated just to help us see how it's thinking that it would bend. We can right click on any of these plots and say animate. And then we can see that animation of whenever it starts to spin, and that's what it thinks it's going to do. But this is exaggerated, so we can see. If we want it to not be exaggerated, I can just clear the deformed result box, and that's what it would actually look like. It's not going to actually bend our fan. From the stress plot, we can see we have not surpassed the yield strength of the material. Our yield strength is like 55 megapascals. We have only seen 28.9. So we're not breaking the blade here. We even have some kind of factor of safety in here. We could probably spin it faster than this and it wouldn't break. Now, what about the displacement? Oh, we moved about 0.22 millimeters at the ends. With these graphs, we can change everything about these graphs also with the full tool. If I edit the definition of this, I can make it show a max flag at the max displacement point. So I can see that red part on the blade displaces about 0.22 millimeters. I could even change the numbering scheme here if I like looking at general numbers better. That's 0.22 millimeters at the ends. I could change the color scheme in here also. If I go under color options, I could change how it's showing these back to us also. We could make it so it doesn't show that deformed shape in here too. We could show the true scale instead of the weird scale that it scaled it to. We could even show different types of displacement. It doesn't have to just be this generic one. It could be just the displacement in a certain direction. But I just did the overall resultant displacement. We can do the same kind of things with the stress plots. We can make additional plots that weren't there yet too. Let me go into settings and tell it that I want to see my mesh. Now we'll see a non-deformed model. This is deformed to the true scale, so it actually only moved 0.22 millimeters. It's not a whole lot. And we see our mesh over top of it. You get a little bit more control over how things look here. And if there's any images that you like that you want to get thrown out to the Microsoft Word report, you can include those images. By default, it takes all of the plots that you have and puts those into the report. But if there's additional images, you can include an image for the report, and it'll throw that into the Microsoft Word report also. Now let me set this up in a way that's going to allow us to be more accurate. If we have a tighter mesh in here, it's going to be more accurate. Remember, I said you don't really know for sure after just one study. You have to run a couple different studies to make sure that your numbers make sense. So we saw a stress value of around, let's say 29 megapascals in this one. Now I'll start a copy of this study. There were some things that I don't want to have to do again. I don't want to have to put the fixture in again. I don't want to have to put the centrifugal force in again. So I can just right click the top of the feature tree and say, hey, copy this study. And in this case, we want to use the cutaway configuration. So I'll use the symmetric configuration. FEA cut. There we go. FEA cut. I want to use the full fan study and make a copy of the full fan study. And I want the new study name to be cut fan. And I want to include the mesh settings that I put in also. I'll show you, we can tell it to be tighter in a certain area than it was. And if we made any changes to the results areas that we want to bring over, we could include the results also. Let's hit the green check. Now I have a new study, cut fan. You can see I just keep getting tabs across the bottom here. And I have to activate the cut fan configuration. That's why everything's grayed out at first. I can right click and activate that, no problem. So we've got our centrifugal force, we've got our fixture. It's telling us we need to remesh. That's what this warning is. We have to add another fixture too, because I have to tell SOLIDWORKS that there's some symmetric action happening out here. So if I right click on fixtures, I'm going to add an advanced fixture. It's going to be the cyclic symmetry. And I just have to grab the faces and the axis that it's going to be symmetric around. And then it knows what else it would have out there. Now it just has to mesh this little corner instead of the whole entire fan. So it's going to be easier for it to solve, meaning we could make the mesh tighter and still have a nice quick solve time. Let's go ahead and add a mesh control. This is another thing we couldn't have done in SimExpress. If I right click the mesh folder, I could tell it, hey, there needs to be a tighter mesh on features, faces, edges, or vertices. So let's say we want a mesh that goes all the way down to 0.75 millimeters along this face. It's going to get tighter along that face now. And I'll choose the create mesh again. Let's see, what did we do last time? 9 and 1.8. That's all the same in here. So that's good. Curvature based. Let's run it. So all the other points of the mesh should look similar, except along this face. It's going to be a lot tighter mesh, meaning our answer should theoretically be more accurate now, since we saw the forces were along this face also. All right, now take a look at our mesh. Look how tight it gets along this face. Before it was really coarse along this face. If we had tried to mesh the whole entire model this tight, it would take longer to run. So that's the advantage to using symmetry. Now, I can run this thing. It takes a couple seconds here, but it should finish out here in a minute. There we go. Now we see we have about 29.7 megapascals this time. It's slightly higher than before, but our answer should be closer to the real world now because we got a tighter mesh involved in here. We might even want to go in and make a mesh control around this fillet where it's even tighter if we want more accuracy. But we can see our answer is pretty close to before. I said around 29. It's only 0.7 megapascals away. That's a good sign that we're converging on an answer around 29. And let's look at the displacement. 0.229 millimeters. So if we're trying to design a hole for this thing to fit in, it needs to be double that and a little bit bigger than that even. So it needs to probably be, let's say, about 0.5 millimeters larger than the diameter of the blade in order to not bind it up in there. We can still show symmetric results. If we want to see this whole entire fan blade, I can edit the definition of this result. And I can come under advanced options and show symmetric results. Bam, we can still look at the entire thing. But now we only had to mesh this little section. So that's an example of a solid mesh with the full simulation package. You can kind of see how that gives you more control over things. Let me go into the next couple things now. So in order to simplify things, when you get into a big assembly file, if you have a mesh that's this tight, it's going to take forever to run. It might take all night to run. So if you're in a big assembly file or have a really big part that you want to simplify, there's two ways you can simplify this stuff. You could use a shell mesh. A shell mesh is for thin featured parts. Think about like things that are sheet metal, something that has a consistent wall thickness the whole way through it. A shell mesh is also called a surface mesh sometimes. It's 2D. Instead of having a 3D pyramid here for an element, now we just have a triangle. There's still a draft quality and a high quality element. The difference is the high quality adds a node in the midpoint, so it has more nodes. High quality still takes a little longer to solve. But you can see now, instead of having a 3D mesh out there, we're just going to have an infinitely thin shell mesh for some items if they're sheet metal. You can still do it as a solid for more accuracy, but if you're trying to simplify things down, you want to make shell meshes when you can. And there's also another type of mesh you can use. If you have welded structures, you can use a beam mesh, which this is the simplest type of mesh that we have. It's going to be like in our engineering study classes when we're trying to see if a bridge is seeing too much force. You take those bridge trusses and just make them into a line, and it has an end point at each end. That's the nodes. This is the simplest type of mesh we can make, but if you have any welded structures in there, it makes things run a lot faster too. So I have this model. It's a particle separator, like let's say like a dust collector, a dust bin or something. And we want to see if the forces that are on it are going to make it fall over. In order to do an assembly that's this large, we're going to have to use some shell mesh. We're going to have to use beam mesh. And we're also going to have to use solid mesh, all in the same environment. But we can do that with the simulation package. So let me get into that model. I'm gonna open up particle separator. There we are. And then I can filter to assembly models so I can clear some of this up. Let's see, I want this particle separator 450. I do already have this study in here, ran also. But I'm going to take you all through the setup just so you can see that you can tell things to be beams or you can tell things to be shells. We'll take you through the setup of this too. So here's our model after it was already ran. We can see the parts folder is way more intense in here. Now we've got little features that look like little shells, little thin surfaces. We've got ones that look like little I-beams. Those are the beam meshes. And there's some more shells. There's some solids still. And if we look at the results, we can only view the results on the beams at one point. So here's the beam stresses. And then if we wanted to look at the stresses on the solids or surface meshes, we could do that also, but we have to have it in a separate plot. So these are the results that we're going to see after I set this thing up anyways. All right, let me go back to the regular model and start a new study. We'll call this one like gravity effects. We're going to add gravity into this too to see if this thing can stand up with its own weight. Plus, there's a motor that's going to hang off of one of these things. So we'll put a weight on one of the beams. There's some special considerations we'll have to make if we have shell meshes on these things. We'll have to add some bonding in to make sure that it glues things together. So you're going to get to see how to kind of really dive in and use this tool. All right, we'll hit OK. And now you can see we have this big old parts folder here. Cyclone parts separator. Everything right now is treated like a solid except for these that were surface bodies in our feature tree. There should be a surface bodies folder somewhere in there. So we actually don't want to take the surface bodies in. They were just used to help model this big thing. I can grab those items and right click and suppress them so they don't get included in the mesh. And then the way they drew all of these things, if you use the weldment tool inside SOLIDWORKS, it'll automatically come in as a beam. If you draw it without the weldment tool, you'll have to tell it to treat it like a beam. They also drew this entire thing without sheet metal tools. So we're going to have to tell it to treat this like a shell also. Let me take a peek at my other feature tree real quick. Oh, they bring a couple things over already as shells. So they started off by making these into shells. I will have to make these into shells if you want to see all that. Let me just see what size they used, I guess. Well, if you ever have one study and you want to copy things over from it, let's say I just want to copy the setup of these parts over. I should be able to just drag this whole thing down over the other tab. And I didn't want to have to make that many shells. I'm still going to make a couple shells for you, but in the example that they show for the one class, they have it kind of preset up. So now our gravity effects tab should have the same things in it as the other folder. So now our shells are copied over because I drug them over the other tab. Check it out. We've got shells in there. That's cool. All right, so that part's taken care of for the first part, no big deal. Now there's some things I want to treat like beams. All of these items, they're going to be like beams. So I'll grab all of these long beams, everything except the gussets and the feet. The gussets we're going to turn into shells, and the feet we're going to leave as solid mesh. So now I grabbed all the beams. I can right click and I can say treat selected bodies as beams. And it'll turn them into little I-beams. We could go back and we could turn them into solids again if we ever wanted more accuracy. We could do that. Now I'm going to turn these 3 gussets into shell meshes instead of solids. If I right click on one, I can say I want to bring in the shell manager. And the shell manager is going to help me tell it that I want these things to be shells. So I want to select the bottom surface of my shells. I want them to be 5 millimeters thick. It's still going to think about their thickness. I'm going to grab this face and hit the green check. I'm going to grab this face and hit the green check. And I'm going to grab this face and hit the green check. And green check again. And we should have shells in there, I think. Let's see. So now, instead of solids, those 3 items are going to be taken like 5 millimeter thick shells. And I have to apply a material to all these parts. I think we want 1020 AISI 1020 steel. I'll apply that. Now all of those parts have the material beside them, so I see they all have a material. And we've got this all set up enough to add the fixtures and all that rest of that stuff. Okay. So because I've turned some things into beams and some things into shells, I'm gonna edit the joint group and hit calculate. See all these little nodes out here? Those are referring to the beam mesh. You can control what happens at those nodes. If you wanted to leave it free to slide along instead of bonded, it is bonded by default. And that's good now for those anyways. Let me collapse this up a little bit. Let's add some bonded interactions. Technically, you would think that these would all get caught, but because we use shell meshes and beam meshes, we might have to go in and add some manual interactions, which you can do. I'm going to add some local interactions, and I'm going to tell it where these things are stuck together like bonded. So now that we have beams, we can grab beams in here. I'll say this beam and this beam are bonded to this shell. And let me add some more of those. I can pin that window open so it stays open, and I can go around and do these. Let me add bonded. I'm going to pin that window open. Beams. This beam and this beam and this face are going to be bonded. And then I'll add another one. I just hit my right clicker to green check that one. This beam and this beam are going to be bonded to this face, and right clicker green check. All right. So I added a couple bonded relations in there. You can see we have local interactions. I'm also going to add some under these feet because these are a solid mesh right now. If I click on it, you can see it highlights it in the feature tree. It's got the solid mesh symbol. We're leaving those as solids. I want to make sure that they get bonded right to these beams though. So I'm going to activate the exploded view that they made for us so we can grab those bottoms of the feet easier. And then I'll add some more local interactions in. Bonded with the beam. So I like to start at the open hole here. This beam is going to be bonded to this face. Pin that open. This beam is going to be bonded to this face. This beam's going to be bonded to this face. And this beam's going to be bonded to this face. Sweet. All right, now we've got a bunch more local interactions added. Just in case something wouldn't get hooked up right, now we made sure that it will. Now we need to add some fixtures. So I'll fix those feet down at the bottom. At the bottom, make sure I grab the bottom face of those. Great. Those are fixed down. And I need to add some forces. So let's add gravity first. We're going to have gravity acting on this thing. I'll right click on external loads and add gravity. We just have to make sure that the arrow is pointing the way that the ground is. So we have to be pointing down. Let's reverse the direction. There we go. And if we wanted to test out a different gravitational constant, like maybe this is a particle separator for Mars or something, we could do that. But it's Earth, so we'll leave it at Earth. And then I'll add some external loads to this back face. We're going to see some loads when we install this thing. We're going to have some forces on this back face. So I'll come under selected direction. I can even add 2 different directions of forces in one go. Now I'll grab a plane for my direction. Let's say we grab that top plane maybe. And I can choose that there's a force going that way of, let's say 50 MPa, or newtons, I mean. And then I could choose that there's some kind of force pushing back on this. Let's say that is of like 75, let's say about 80 newtons for that one. So there's a force pushing back on it, normal to the plane. Let's say that's about 80. All right. So I added a force there, but now it's got 2 components to it. We can see there's 2 arrows on there. We've got our gravity, we've got a fixture, and we are going to have a motor kind of hanging off of this beam. See these bolt holes? Well, let me just add one more load. There's going to be a force on that beam of 150 newtons. So now I can add a force to an entire beam. I'll grab that beam. It's going to be along a selected direction also. Make sure my force is pushing downward here. And that's going to be 150 newtons. Maybe there's like a motor bolted on the side or something. It's not pictured here. All right, and now one more thing we might want to do, we could add mesh control to beams. Even though they're taking it as a simple line, it's able to break them up into sections and tell us the force at each section. I'm going to add a mesh control to those few beams. We need to have a beam mesh control. and I want it to have a break line every 5 millimeters on these beams. All right. Okay. And we're ready to mesh this whole entire model now. Sorry, I'm kind of running up to the wire, but I think we'll get done with enough time to talk about this for a few minutes still. All right, let's create a mesh. I want to use a standard type mesh this time. Okay, with a global size of 25 millimeters. You'll get to see some surface and beam meshes all in the same world here. All right, now the beam meshes come in at first all looking like a circular tube. The surface meshes come in looking like an infinitely thin surface too. We have to look at our model and make sure that there's not any gray faces. You can see, oh, that's a gray face there. That means my mesh is flipped on this face. If I click on it, I can right click on the mesh folder then and try to flip that shell element. You want to try to make sure your shell elements have the same faces pointing all the way everywhere. So that's one thing we got going for us. I could render the beams if I want to still see the shape that they are. I could right click on the quality folder and say render beams and shells in 3D, and it'll give me their shape. And it'll give the shell thickness, even though it's infinitely thin. And I would say we're ready to run this thing. Let me hit run this study. It's going to go through and spit out some results for us. At first, the results have to be on either the beams or the solids and shells. So we could look at just the beams at first, and we could look at the axial, upper bound bending, upper bound, see all these different options. We're just going to look at the axial forces at first. If we choose render beam profile, the beams will even be the right shape, and you get some different choices. Maybe we look at axial and bending stresses. There we can see in this one, we've only seen about 1 megapascal, and the yield strength is up at 351. So it seems like this thing's strong enough for this at first. We could also show results for just the mesh. So I'm going to right click my results folder and add a whole brand new stress plot here. It'll be on the solids and shells, von Mises stresses. It's going to be taking a look at the top of the shell meshes first. We could grab the bottom of the shell mesh face, or we could choose render shell thicknesses in 3D if we want to try to see the top and the bottom at the same time. And I'm going to turn my scale to the true scale instead of this weird deformation. Let's see what that looks like for us. Something funny's going on with that. So it should look something like this. Just flip to the finished one. It should be more like this. And we should still see that we're rather low with our stresses. The highest point of stress was right at this connection area where it hits right in there. And it's still only about 16 megapascals. Our yield strength is way up at 351. So we don't see anything super concerning with these forces. All right, that is where I wanted to be today. do you all have any questions for me or anything that you'd like to see differently at a different date? Sorry, I haven't looked up until now. I'll look and see if we've got any questions. Zoom assistant. Oh, there's the chat. Okay, I found it. All right. Hello, everyone there. Is there any machine learning model employed by SolidWorks that is helping to eliminate the back and forth computational times and costs? Not to my knowledge, but there are some blind spots for me in this area still. So especially in that area, I'm gonna have to ask about that machine learning to help eliminate all the. So yeah, that's a great question. I'm not 100% sure. Can you share the assemblies for practice? Yes, absolutely. I'm going to share this file set with Derek. And if you want it after that, let Derek know. Derek will make sure you guys get this file set. It'll have the particle separator in it, and it'll also have the hand wheel and the fan blade in it. So you could try out any of this stuff. If you have the recording, you could go through and try it out too. Say I'm doing an analysis on a pressure relief valve. Does SolidWorks have appropriate tools for computational fluid dynamics analysis? So yes, they have a flow simulation also. You can do flow simulation inside of SolidWorks, and it can take care of most of your CFD needs. Depending on where you want to be at, though, like I had a question in the last meeting about if you had like a hydraulic shock and you wanted to see how much dampening the hydraulics have in that, you might have to get into so we have the 3D Experience platform, and it has some more powerful simulation tools on it from Somalia. So depending on if you want to like see how much spring pressure like a fluid has or something like that, if you're trying to move the fluid and see the forces in the fluid, then you might have to go up to the 3D Experience Somalia package, but it works kind of in a similar way. And let me see. I have these features. How do I start from the beginning? For right at first, I would so you have Sim Premium, Sim Professional, and Simulation Premium. That's awesome. Any of those ones that you add in on your drop down will allow you to do what you've seen today. They'll all allow you to set up a static simulation study like we've shown. The difference is that your simulation premium is going to let you do some nonlinear things, like if you wanted to try to see maybe how much rubber bounces back after it gets hit by something, or if you bend something, how much does it stay bent? You could try to figure that stuff out with Sim Premium. The other ones will just be limited to static linear analysis. And the easiest way, if you're just trying to do one part, the easiest way to start out is to start out with the Sim Express Wizard. It's really fail-proof. It'll walk you through all the steps. I would say that's probably the easiest way to start. So try that hand wheel model and Sim Express. And then any of those add-ins that you have will let you do what I showed today. They all have the simulation advisor too, and the sim advisor will try to help you if you're not sure which kind of study to pick. It'll try to help you with that. There are great questions out there. Let me see what we get any other. How do I start preparing for CSWA simulation? So we have a simulation class that gets you ready for it. But there are videos on YouTube about it too. So let me see where they put it. They reorganized my sheet here. Blah, blah, blah. simulation. Oh, there. Okay. So we have this simulation essentials course that's 3 days long. It takes you through static simulation, which is the stuff I was talking about today, static linear simulation. This is also all you'll see on the CSWA sim. So the first sim study, this kind of stuff that I've been teaching you guys today is all that they really get into on that. Then there's the simulation professional cert, and that gets into other things like drop tests and frequency studies and buckling studies and different things like that. So it gets into the rest of the tools that are in the simulation professional realm. And then that's where I actually don't teach beyond that. I only teach these classes, and then I don't teach any more yet. So we have other people that teach these additional classes that know more about it than I do. But I kind of stop it there. But there are YouTube videos. I would look up like CSWA Sim on YouTube and see what they've got to offer. Also, they might try to go through the exact questions that are on the test. In our course, we don't go through the exact questions, but we get you prepared otherwise. So I would look at YouTube also for that. And is it possible to generate a video of simulation that can be suitable for presentation? I think so. So you can, if you do the animation, if I wanted to animate my stress results, so it's going to try to show that animation right now. Remember, I have it on true scale, so it's not overly deforming things. We could save this out as a video file, and then we could show them how it's deforming. So if you liked like how that hand wheel was deforming or something like that, you can save that out to show that. And let me see, there's another question here. Hi. Import thermal data or other forms that affect stresses on. Yes, yeah. So let me just show you how you would import that before I leave today. But so you can set up a thermal study on things. When you're defining a new study, you can set up a thermal study. A thermal study is looking for the temperature that something gets to. So for example, in our course, we have a thermal study that we set up where we try to find what the temperature of a computer chip is based on the wattage of the thing that's on the chip. So we say something has like 25 watts of power, and then we tell it maybe you can tell it how long it runs for, or you can see what its maximum temp would be if it ran all day. So we would find out what its temp would be, and then we could start a static study and import the thermal effects. If I start a new static study, anytime you want to import thermal effects into a stress study, you just have to right-click the top of the tree and go to the properties of the study. And then in there, there's a flow thermal effects tab. It'll let you bring in temperatures from a thermal study, and you can pick which study you have on the tab below, and it'll bring those temperatures into this new static study. So you can compare that. You can also import things from flow studies. You can bring those into a static stress analysis also. These are great questions, everyone. I don't see any more popping up though. So let me know if you have any additional questions. And if you have specific topics you'd like to see for next time, let Derek know. We could try to do a simulation on a certain type of thing. It could be more specific for you. If it's beyond my knowledge, we could even have someone else from TriMech do it. I know a lady, Sumon, She's been working in simulation for over 25 years. It's all she does. She knows this stuff way better than I do too. So if you have hard questions, I usually go to her. But thanks everybody. That's all I got for you for today. I hope you have a good rest of your evening. Thanks for having me.